Hello and welcome to this video on aromaticity. My name is Kim, and in this video we'll be identifying the characteristics of what makes a compound aromatic. Aromatic compounds are prevalent in organic chemistry for reasons we'll discuss in a later slide. There are strict guidelines that must be followed for a compound to be considered aromatic. It must be cyclic and it must be planar. The molecule is planar because of the system of delocalized electrons caused by conjugation. Conjugation means that there is a free pi electron on each of the contiguous atoms in the cyclic molecule, and the system of pi electrons delocalize through the whole ring. For example, there is a pi electron being contributed by each carbon atom in furan, and 2 pi electrons being contributed by the oxygen, leaving the other pair of electrons free. Notice the total number of pi electrons. It's 6, which brings us to the final condition. The number of pi electrons participating in conjugation must follow Huckel's rule, which is 4n plus 2, where n is a positive integer. Aromatic compounds will have 6, 10, 14, 18, and so on pi electrons. There exists a very small subset of compounds that appear to be aromatic but have one special difference that contributes drastically to its stability compared to aromatic compounds, and that is anti-aromatic compounds. Anti-aromatic compounds are cyclic, planar, and conjugated but have a different number of pi electrons. They follow 4n, where n equals a positive integer. So anti-aromatic compounds will have 4, 8, 12, 16, and so on pi electrons. Briefly, the reason why anti-aromatic compounds are unstable is because you have a half-filled shell, and often the molecule will rearrange itself to create full shells, hence the instability. With aromatic compounds, 4n plus 2 electrons create full shells of electrons. Finally, a non-aromatic compound will fail any one of the first 3 criteria, and failing any criteria means we don't really need to consider the number of pi electrons. Why are aromatic compounds so common? It has to do with its unusual stability. As discussed earlier, there are delocalized pi electrons that encompass the whole cyclic structure. For example, I have on screen benzene, the prototypical aromatic compound. If I push it to its side and visualize the pi electrons, each carbon has 2 sp2 bonds and 1 sp2 bond to a hydrogen, which I didn't draw in for the full molecule. Each carbon also has a free pi electron, which can be visualized by the balloons above and below the ring. The pi electrons don't stay put though. Because they're all in the same plane, the electrons delocalize, forming a ring above and below the plane of the ring. Kind of like those sticky hole punch reinforcement O-rings that you can put in your notebook paper. It makes it much stronger, which is what's contributing to the stability. Let's use the information we reviewed and classify the following molecules as aromatic, anti-aromatic, or non-aromatic. We just saw the molecule in A, benzene, on the previous slide, but let's go ahead and verify that it fulfills all 4 criteria of aromaticity. Benzene is definitely cyclic and is conjugated since all 6 carbons contribute 1 pi electron. And it is also planar because of that conjugation. There are 6 carbons, each contributing 1 pi electron, which means that it does fulfill Huckel's rule, 4n plus 2. Benzene is definitely aromatic. The molecule in B is biphenyline, which is definitely cyclic. It also has all carbons with a free pi electron that can participate in the double bonds, and are continuous along the entire molecule, making the molecule both conjugated and planar. Each carbon contributes 1 pi electron, and if you count, you can see that there are 12 pi electrons. This does not fulfill Huckel's rule, but actually the rule for anti-aromaticity, 4n. Therefore, biphenyline is an example of an anti-aromatic compound. The molecule in C is cyclohexane, which is cyclic. However, all the carbons are sp3 hybridized, and therefore no conjugation is occurring. Since it fails one of the criteria, cyclohexane is not aromatic. The last molecule in D is methyl benzene, or more commonly known as toluene. The molecule is cyclic, with a pi electron from each carbon participating in conjugation, and is therefore also planar. All 6 carbons contribute 1 pi electron, so it fulfills Huckel's rule. This compound is aromatic. Don't be fooled by the addition of a methyl group. Remember that the benzene we saw in A has an sp2 bond to a hydrogen, and all we've done is swapped out the hydrogen for a methyl, which does not affect the aromaticity. Being able to predict aromaticity is a big step in predicting the reactivity of molecules in organic chemistry reactions. This is a great skill, so make sure you follow up with practice.